here, and I would like to add my thanks to the organizers for the invitation to come to this excellent meeting. I'm going to be giving 2 Blackboard lectures and then a talk in my third slot on Thursday. Because I'm not very good at drawing maps, I will wait until Thursday to show you where St Andrews and Scotland are. But what I want to do to start is to give a kind of overview of the things I'm going to try and talk about in all of these lectures to give you some outline, some roadmap of where we're going. So the idea of today's lecture is that I'm going to talk about Dicke and superradiance, i.e. what Dicke actually talked about in terms of superradiance, although I will not put it in exactly the language that he used. And then I will talk about the Dicke model, which he didn't actually introduce in the paper that talked about superradiance, but was introduced later by Hepp and Lieb. And I will then talk about the phase transition in this model to a state which is known as a superradiant state, or steady state superradiance. And I will finish today's lecture by talking, hopefully if I get time to get there, about the question mark of does this transition exist? I will probably stop at that point in today's lecture, and then in tomorrow's lecture what I will talk about is answering that question, but not in the steady state. So I will talk about ways of making the Dicke model phase transition that I talk about today, or at least making physics related to that show up, but not exactly in the context that I'm going to talk about it today. And most of tomorrow's lecture will be about various different ways that there are to get around this issue I'll raise at the end of today's lecture of whether the phase transition really exists. And then what I want to talk about in my third lecture, which will actually be a talk rather than a lecture, is cold atoms in optical cavities specifically, and the physics related to the Dicke model and superradiance that you can study with that kind of system. So that's the roadmap of what I'm going to try and say over the 3 lectures. Do please stop me if there are questions. In order to start this journey, I was trying to think exactly how far back I should go, and I haven't gone quite as far back as I possibly could, which would probably be to write down the Lagrangian describing Maxwell's equations. But I'm going to start not that far further forward by writing down the Hamiltonian for matter plus light in the Coulomb gauge. And I will write everything that follows in the Coulomb gauge, and at some point in tomorrow's lecture, this may turn out to matter if I have time to cover that point. But the point in the Coulomb gauge is that I have a Hamiltonian where the coupling between matter and light is the standard minimal coupling that says that for each particle alpha, what I get is the momentum of that particle alpha minus charge of that particle alpha times the vector potential evaluated at the position of particle alpha. And in the Coulomb gauge, I should also say there is a direct interaction between charges, the Coulomb interaction, and between this static Coulomb interaction and the coupling to the vector potential, from the combination of those two, you get the full light matter coupling with retardation effects and so on, but individually these bits look like instantaneous interactions. And then, of course, there is a third part, which I will write as epsilon naught over 2, and I'll write this in momentum space as a sum of c squared, k squared, times the kth component of the vector potential, plus the conjugate momentum to the vector potential. And the reason for writing this Hamiltonian to start with, and not just starting with a form of a Dicke model, is to try to make clear what are the approximations and the assumptions that go from that to the model that I'm going to talk about, in particular so that when I talk about the question of whether phase transition really exists, it will be clear what it is I'm returning to in terms of the original Hamiltonian. So what one then does with this is make a series of approximations So there are approximations such as the dipole approximation, which means that when I look at this interaction between matter and light, I believe I have some small object, some atoms where I can ignore the variation of the electromagnetic field across the length scale of the atom, and so I can divide all of the charges up into sets, and one set describes one atom, and then I can turn all my sums into a sum over atoms and sum over the charges within an atom, and within an atom I can replace this coordinate dependence by what's the value of a vector potential at a particular position of an atom. And when I do that, I will get a picture that says the Hamiltonian can be written as a bit which I will call the Hamiltonian of atoms, and that will include the bare potential, the bare kinetic energy for all of the charges in the atom and all of the static Coulomb interactions within an atom. And I will also then write next this term, the electromagnetic field energy, in a much simpler form. So if I just notice that this is a quadratic Hamiltonian in terms of a vector potential A and its conjugate momentum, then that's exactly the Hamiltonian of a harmonic oscillator. So I can always rewrite that in terms of harmonic oscillator raising and lowering operators. And because I forgot to mention, this is in the Coulomb gauge, and so K dot AK, the vector potential at momentum K, is 0. I only have two independent polarization components, so I get this Hamiltonian for the modes of light. And then the interesting bit all comes from how does the matter interact with the light. And if I look at the remaining terms here, what I should write is a term that comes from minus P dot A, and that will look like a sum over atoms times a sum over all of the charges within an atom. So I'll write Q alpha P alpha I over M alpha. So that's all of the charges within one atom give me this dipole moment, which I then multiply by vector potential at the position of atom I, and for completeness I should also include the other term, sum over all atoms, sum over all charges in an atom, Q alpha squared over 2m alpha, times the vector potential at the position of that atom squared. So that gives me a slightly simpler form, and what I should then also do is say that if I've written here things in terms of raising and lowering operators, I need to define that these vector potentials can be written in terms of these raising and lowering operators, and I will write this as sum over K and sigma of a symbol that I will use just as shorthand for the combination 1 over 2 epsilon naught omega K, C mod K, times the volume that I'm working in, times A K sigma e to the I K dot Ri, so this is A of Ri, plus summation conjugate, times a polarization vector. And so in principle that contains all of the same information that I had in the original Hamiltonian now, but written in a form that will make it easier to then make even more approximations. And so the other approximations I'm going to make are the approximation of describing atoms as two-level systems, the approximation of ignoring this quadratic term as being a small effect, at least at low densities, and the approximation of the rotating wave approximation, which I'll discuss in a little more detail in a second. But if I just start from the first couple of those, then if I replace this H of atoms, this slightly unknown thing that's containing all of the kinetic energy and the electromagnetic potential energy, describing the physics of a single atom, and say atoms have discrete energy levels, what I can then do is write a Hamiltonian that is a sum over the atoms of whatever is the energy of one atom times sigma Iz, which will describe a two-level system describing the two states of this atom, plus a sum over momentum states of C mod K A dagger K sigma, A K sigma, and then I will have a term which describes the interaction between atoms and photons that will look like sum over atoms and photons, and in principle over polarizations, and there will be some interaction constant, I'll come back to that in a second, times sigma ix, which describes transitions between different states of this two-level atom, and then I should multiply this by a k sigma e to the I k dot ri plus emission conjugate, and this GIK contains all of the physics of this calligraphic A for the strength of the electromagnetic field associated with creating one photon, and also the question of what's the overlap between the polarization vector and this sum over all of the charges within an atom, Q alpha, P alpha over M alpha. And so this describes all of the strength of this electromagnetic coupling. And what I said I wanted to do first in this sequence of things was to talk about what it was that actually Dicke discussed in terms of superradiance to begin with, and then go on to talk about the Dicke model. And that's why, so far, I haven't done anything about restricting the number of photon modes, because actually the paper in 1954 by Dicke, which talked first about this idea of superradiance, was really starting from a model very much like this of atoms in free space, and asking about the process of collective decay versus individual decay. Yep. So the idea of this two-level system is to say that an atom will have some discrete energy levels, and then there'll be some continuum states above some energy. And what I'm going to do is just describe these two lowest levels of the atom. Now, if I think about real atoms, then maybe I have to worry that in many real atoms there might be some degeneracy because these would be p orbitals. But I'm going to look at a simplified picture where there is just a two-level system here. And perhaps I should also then comment, but I've written this as sigma ix because this has got matrix elements here between the lowest two levels of the atom. And what this is saying is this is the matrix element for the momentum operator, P, for the charges in the atom, to cause transitions between these two lowest levels. There might, in principle, have been terms which involved 0, 0, but actually if I have a parity symmetric problem, then there is no matrix element of a momentum operator between eigenstates of the same parity. So that's why I can say that this will look like sigma x. It will only have off-diagonal elements. Any other questions? Okay. So I'm going to give a very brief summary of what it was that Dicke originally said about superradiance, because already there have been several talks, in particular Barry Garraway's talk, that introduced a lot of the mechanism that I would need in order to describe this, which is to write down a master equation integrating out the effect of this continuum of photon modes. And the point that Dicke made in his paper in 1954 is there are two kind of quite different master equations I could think of as limiting forms that come out of this. And they depend on what I think is the effect of these phase factors here. So one approximation which you might make if you had atoms which are far apart is to say, I will assume that whenever I have sums over momentum of e to the I k dot ri minus rj, that this will go to 0. And this is the approximation that will lead you to saying atoms behave independently, because as soon as this statement is taken to be true, then what that will tell me is that if I start to do the calculation where I treat this term in the Hamiltonian as a perturbation, and I write out a master equation, and I trace out the Barth modes, the only contributions I will get when I do that trace over Barth modes are terms which involve the same atomic operator appearing twice. If I have two different atomic operators, I'm always going to get something like this, which involves the sum over all momentum states of phase factors for different atoms. And so what that then gives you is a master equation that looks like some terms from a Hamiltonian that I'll ignore, plus a dissipation term, which looks like the individual dissipation of each two-level system. And so this also is the model that Derek Chang spoke about yesterday as the thing you find in textbooks as a starting point, but which is not always correct. And it's not always correct precisely because it's only correct if you can make this approximation. And we heard in detail what happens when you treat these phase factors precisely. But the thing that Dicke pointed out was there was indeed another limit. And in order to illustrate this, he looked at the other extreme limit, which is where you say, what happens if I put all of the atoms close together? And I mean close together in the sense that when you have a transition here, you will create photons, and mostly you will create photons which have an energy that roughly matches the energy of the atomic transition. So there will be a characteristic wavelength, and you can ask what happens if that characteristic wavelength is not comparable with the spacing between the atoms, but much longer, so that you work in a limit where all of these atoms see the relevant modes of light with the same phase. And so that corresponds to making a different approximation that e to the I k dot Ri minus Rj is equal to 1. And in that case, when you do the derivation of the master equation and you trace out all of the bath modes, you keep everything because there are no phase factors. Every phase factor just turns into 1. And so what you get is something that looks similar to this, but rather than having individual decay, what you have is L, so I should write gamma over 2, L of sum over all two-level system, so over all atoms, of a collective decay operator. So I should just point out for completeness what I mean by L of X is this standard Lindblad operator. So that what I'm describing here is decay of each individual atom, and here I'm describing the decay of a collective spin. And if you then go through this treatment, so this is not the language that Dicke used in his original paper, but this is the same idea. If you go through this treatment and ask what happens for decay with this form A versus decay with this form B, so if you assume what are independent? The alpha, you mean, so this is supposed to be a calligraphic L? Okay, this is the calligraphic L that's describing this Lindblad operator. So the difference between these terms is here the sum is outside. So I have a sum over I, and if I write it out, I will get, in this case, I will get sigma I minus rho sigma I plus, minus, yeah. So the crucial difference is that if I do it this way round, then I only have terms with the same I in both places. But whereas if I do the second form, I will get that because the sum is inside, I get sum over all I times sum over all j for some different j, and then I get all possible cross terms. Okay, yeah. Were there any other questions? Yep. Yes, sorry, I shouldn't really write it. I am continuously inconsistent whether I stick the half here or here, and I seem to have stuck it in both places. But you're right. If I write this with this form, I shouldn't put a half here. Yeah. So in deriving this, when you trace out the bath, you have to make some assumption about the original state of the radiation modes, and to get this pure decay form, I'm assuming they're empty. And this is a reasonable approximation for atomic transitions because you're talking about energies of 1 electron volt, which in temperature is 10,000 Kelvin, so there are no real photons around at that kind of energy. Okay. Yeah, so if I take the two forms of decay that I wrote here and ask what would I see for the number of photons coming out of the cavity as a function of time. So if I call this the intensity of light as a function of time, in the first case, if I have n atoms, what will happen is they will all act independently. and I will see that each atom has some exponential decay, so the light intensity will fall off exponentially with a time constant that's given by 1 over gamma, and this is the behavior of independent radiation sources. If I do the same thing for case B, where I assume all the atoms act collectively, then you find something very different occurs. You find, now I can't draw these on the same scale, so this is I of t or proportional to I of t up to some constant, because if I try and draw this on the same scale, I would end up going off the top of the blackboard. But what you find is that there is a curve that looks something like this, and there is a time scale where there is a maximum intensity of radiation, and this scales like 1 over the number of atoms that you have, and this peak radiation on this scale, so this is the curve B, this is the curve B, this peak scale of radiation goes like n squared, whereas in contrast, this peak is of order n. So what this says is that in the case of the atoms that act independently, you get the maximum radiation is just n times what it would have been with one atom. But when they act collectively, there is this n squared factor, and the n squared factor in the rate of emission is cancelled by the fact that the emission is faster, so the total amount of light that comes out is still n photons. So this is describing, I should have said, this is describing what happens if I prepare an initial state with all the atoms being excited, and then just ask how radiation leaks out of the cavity. And so this characteristic difference, this extra factor of n, is what was first called superradiance. And it's really this idea that when atoms interact, there can be this constructive interference in the transition between atoms, in the transitions, that leads to this enhanced rate of emission. The width also depends on the number of atoms. There is a slightly more complicated dependence, but and actually, so you can make a very good treatment of this. So I'll have a brief diversion by saying that what appears here you can think of as being a collective spin operator. So I can write that actually this is some giant spin, and because it's a giant spin, because it's a spin with magnitude n, its dynamics will be pretty much the dynamics of a classical spin. And so if you actually then solve this problem, but you can write down classical equations of motion for this collective spin, and what you find is that the classical equations of motion will tell you that the spin, if it was slightly destabilized from pointing exactly up, will do this and point down, and this spike in radiation is when the spin is moving fastest near the equator. The subtlety comes that actually this initial bit around here requires a full quantum treatment, because you need to describe the physics of why it is that a spin pointing directly up is actually not metastable but is unstable because quantum fluctuations drive it away from this inverted state. So there's a slight subtlety about how this initial behavior grows, but once it's taken off, then the behavior can be described pretty much classically. It does. The Hamiltonian does. What doesn't is writing classical equations of motion for the spin. So everything I've written so far would describe the full physics. It's just, but if I then tried to say, well, let me just write a classical equation of motion, you'd find an equation of motion where if you added by hand some noise, if you did something like use Wigner-distributed initial conditions, you get exactly the right physics, but you do need to include those quantum fluctuations. They're there in a Hamiltonian, they're there in this master equation, but they wouldn't be there in a classical treatment. So the two-level approximation holds reasonably here as long as there are not any other resonant transitions that you have to worry about. And when I talk about excited initial state, what I would really mean is prepare all of the atoms into this kind of state here. And that's something you can do in principle. You can apply a Rabi pi pulse, or you can do adiabatic rapid passage to invert an atomic transition on one particular line, as long, and particularly in this kind of setup, you would have to go through a sequence of transitions to get to higher order states. So it is fairly feasible to imagine preparing this state where all of the atoms are in this first excited state, and then you don't have to worry about higher states. So another way to understand this other one is to say that because I have ignored the phase factors, there is no which way information about which atom decayed. So I start with n excited atoms, and then I have one photon comes out, but I don't know which atom was the one which was the source of the photon, because that information would have required I had phase information to locate which atom was which. So after one photon has left, what I will have in the collective decay, I will have this superposition of n-1 excited atoms and one unexcited, but I'll have all states of this symmetrically, and then I get constructive interference between these different de-excitation pathways. You will, I think, so I don't know what value you start seeing a peak at. I know that 5 or 6 already starts to show something. I've never actually tried to check whether the critical number is 2 or 3 or... typically you want to think about n being large enough that you can really see significant changes in the timescales. So that was the first thing that I wanted to talk about, was this original idea of superradiance. And as I said at the start, this is not the thing I'm actually going to talk about for most. So is that a question? Okay. So, the thing I'm going to talk about for most of these lectures is not this idea of superradiance, but is another thing which gets called superradiance. I should perhaps comment there are many things that get called superradiance. I'm only talking about 2 of them. The thing that I really want to talk about for most of these lectures is the phase transition in the Dicke model. And this is considering a different Hamiltonian from the one that I've been thinking about so far, which is to say, what happens if I try to modify the electromagnetic energy density and density of states by putting atoms into a cavity? And so the cartoon I'm going to draw is my theorist's cartoon of a cavity with some atoms in it. And one great thing about a cavity is that I can control which modes of light there are that talk to the atoms, and I can make it for those modes of light which do talk to the atoms, you get relatively high field strengths by confining the light into a cavity. So I want to consider the case where I put a cloud of atoms in a cavity and then have them coupled to a single mode of light in the cavity. And this will lead me to the thing which gets called the Dicke model, although as far as I understand, it wasn't really written down until a paper by Hepp and Lieb that talked about the phase transition in this model, which wrote down this Hamiltonian. So I have a sum over atoms, omega naught over 2 sigma iz as before. I have only a single cavity mode, so I'll write omega a dagger a, and I'll stop worrying about polarizations. And then I have the light matter coupling, which will look like G times sigma ix times a plus a dagger. So it's just taking the Hamiltonian that I wrote down as the one which leads to this radiative decay, but now saying I have a single mode of light in the cavity. And of course, with this kind of model, I'll get very different kinds of behavior. If I did exactly the same experiment as described here of preparing all the atoms in their excited state and looking at the subsequent time evolution of this problem, you also get a form of superradiance that I'm not going to discuss in any great detail, which is the fact that the number of photons inside the cavity as a function of time shows a fast decay and then subsequent revivals. And you get revivals because this is a closed system. I have just one cavity mode and one set of atoms. And the time scale for these oscillations is also something that goes like 1 over n. So as you have put more and more atoms in the cavity, these oscillations get faster. And you could think of that as the closed system limit of this as an open system result. And actually, there's some quite good matches you can actually understand. In fact, I shouldn't say 1 over n, I should say 1 over root n. And the difference between the 1 over n and the 1 over root n is exactly the difference between coherent and incoherent dynamics. But this is not the thing I want to really talk about. What I want to talk about is the phase diagram of this model. And because it's often discussed in this context, I also want to talk about the phase diagram of not just this model, but a closely related model, which is the Tavis-Cummings model. And the Tavis-Cummings model is the same Hamiltonian up to this last term, but where I replace this by the rotating wave approximation for this Hamiltonian. So that means that I look at the two terms in this, the terms which create photons and the terms which destroy photons, and say that if I have a system where omega and omega naught are fairly similar, then if I want to create a photon, there will be two processes I can do. I can have a transition of the atom from up to down or from down to up, and one of these processes will be nearly resonant and the other one won't be. And the rotating wave approximation says, let me just keep those processes which are resonant. And this can simplify the dynamics, particularly because once you take this approximation, there is a conserved quantity in this Hamiltonian, which is the number of excitations, the number of photons plus the number of excited two-level systems, and that allows you to simplify the dynamics. In talking about the phase diagram, I will tell you about results for both of these models. Most things behave very similarly. Actually, no. So the picture that I guess, did everyone hear the question? The question is, do these oscillations die away in time as n goes to infinity due to thermalization? So they don't, in the sense that this is a closed system and there's a very small number of modes and a lot of conserved quantities. Actually, if you really solve the quantum dynamics of this problem, the behavior is actually opposite, that small n, the oscillations die away, but for large n, the oscillations persist, the oscillations persist for a time scale that goes like the logarithm of n. So as n goes to infinity, actually these oscillations do carry on forever. And the point is that these oscillations are really from a semi-classical treatment of this model, and that semi-classical treatment is only valid in the large n limit. And what you find, I mean, if you want to solve it quantum mechanically, what you find is that as n goes to infinity, the energy spectrum of this model becomes very regular, and therefore you get persistent oscillations. But there's a finite system case where they wash out. Yes, so I want to avoid being drawn down too much of a diversion. There's a whole family of models related to this which do show persistent oscillations. They are ones which are classically integrable, and it turns out that there are two kinds of things you can do. You can treat models where so the thing which you can easily do is actually generalize this to a case where these energies are not the same. And in that case, you can't write it in terms of total spin, but there is still a whole set of conserved quantities. You can write down lax vectors of what's conserved, and the classical dynamics are completely integrable. And that integrability allows you to show that the oscillations, at least classically, survive for all times. If you make this G disordered, that no longer holds, although actually there's a class of models with arbitrary Gs which are still integrable, but then they start to get direct spin-spin interactions. I'm not aware of any particularly close relation. So in a normal model of a normal textbook laser, you have strong dephasing of the lasing gain medium. You're in a regime that it's hard to maintain phase coherence between different superposition states. So the mechanism that is present here and leading to this enhanced emission isn't normally present. Because the other way of saying that is the mechanism which in a typical laser leads to this enhanced radiation is the stimulated emission into the photon modes. Here I have that when a photon is emitted, it goes away and never comes back. And nonetheless, you get this enhanced emission because of coherence in the atoms. So there is a third category of thing you could talk about, which is a laser which has coherence of the atoms, and then that lies halfway between these two. But there are two extreme limits you can consider, one which has strong dephasing of atoms of gain medium, but has a cavity mode and has stimulated emission causing enhanced radiation. And the other thing which is clearly separate is this superradiance phenomena, But there are definitely things that you can put in the middle of this continuum, including things like superradiant lasers where you have a bad cavity but allow coherence. No, so here, in this process, you're putting photons into a continuum of modes. So, and you're putting them in a continuum of modes and they're coming out as a function of time. So you will have a state where there will be some distribution of time events at which the photons would reach a detector. And I don't think you can, I mean, you can start to ask questions about the statistics of the photons, but it's not any simple state. It's n photons in lots of different modes. Okay. So let me skip that. So what I want to talk about really for the remainder of this lecture and in all of that follows is the fact that this Hamiltonian has a phase transition. And it has a phase transition which occurs when the matter-light coupling becomes large enough. And the basic picture is to look at the two parts of this as being in competition with each other. If I think about the ground state of this Hamiltonian, if I look at the first part, it's clear that the ground state would be to have no photons because they cost energy, and to have all the two-level systems pointing down because exciting them costs energy. Whereas this second part would prefer to have a coherent state of photons, so that this has an expectation, and to have a coherent polarization of the atoms, so that they're in some superposition of up and down. And if these two terms have opposite signs, then you will minimize the energy, and you will end up in a state which has coherent light in the cavity, but that will only occur when this bit of the Hamiltonian beats the first term. And there's a relatively straightforward way of trying to see when this phase transition occurs, which is to make use of the fact that, as we did over there, and as I commented in response to Marco's question, you can, in the Hamiltonian that I've written so far, write this problem in terms of a giant spin. You can define a spin operator which is a half of the sum over all atoms of the Pauli the vector of Pauli matrices, and you can see that this Hamiltonian depends only on this collective S. And why that's useful for getting a simple treatment of this is that there are approximations you can make for large spins based on ways of rewriting spins in terms of bosonic operators. In particular, if I write the spin raising operator in terms of a bosonic creation operator, with a factor square root 2s minus b dagger b, and I write the spin counting operator as minus s plus b dagger b, this transformation, the Holstein-Primakov transformation, allows me to turn this into a problem of bosonic mode A interacting with bosonic mode B, and then to make various statements about where the phase transition will occur. And the idea of this transformation physically is to say what B does is counts excitations of this giant spin. So if there are no B's, then Sz is minus S, it's maximally pointing down. As I create B's, I excite this spin and I get a higher value of Sz. And what this square root factor does is says that as you increase S, at some point you can't increase it any further. Specifically when B dagger B is equal to 2S, the spin raising operator no longer does anything. Mathematically, the crucial thing that this actually does is ensures that you get the right spin commutation relations. So if you write this in terms, if you write out commutation relations in terms of the bosons, what it means is that the bosonic commutation relation B dagger B is equal to 1 becomes consistent with the statements you would like to have about Sx, Sy being ISZ and so on that you would need in order to describe spins. So was there a question? Yeah. You can't see. Okay. I will go back to the other side. Can I write one more line here because otherwise you're going to be looking at both sides of the board simultaneously? Holstein-Primakov. So the one more thing I want to say is what you can then often do is to make an approximation where you say this term is actually like B dagger square root 2s, in the case where the number of bosonic excitations is small compared to square root 2s, this will not describe the full physics, but it will be good for instance, describing the vacuum state or the ground state when G is small. And I should also point out that with this definition of S, the collective spin is equal to n over 2, where n is the number of atoms, because of this factor of a half in front of Pauli matrices to turn things into spin operators. It doesn't work. So you will get that the S plus and S minus no longer have the right commutation relation. They have a commutation relation which I think will turn into just minus S, whereas what it Sx and S, well, so S plus and S minus should have a commutator which is 2SZ. SZ should have this form. If you ignore this, if you ignore this B dagger B, I think you just get the minus S part and you don't get this part. So it's an approximation which is only valid as long as the number of B's is small compared to the size of the spin. Okay, so the trick I want to use is this Holstein-Primakov approximation plus approximation for large S or small number of bosons. And let me do this first for the Tavis-Cummings model rather than the Dicke model, because this answer is more straightforward. What I can say is that the Tavis-Cummings model will look like omega naught times B dagger B plus omega times A dagger A plus G root n times A dagger B plus B dagger A plus some terms which are either constants that I've thrown away because they don't do anything, or higher order terms in this expansion of the square root. So the crucial things I've done is say that the energy of exciting one of the two-level systems turns into the energy of exciting SZ. So this B dagger B counts the number of excited spins, and that's the cost of exciting atoms. And then what you have here is just a coupling between two bosonic modes. And it's very straightforward to diagonalize this problem. You can write that this will turn into something I'll call omega minus C dagger C plus omega plus D dagger D, where omega plus and omega minus are eigenvalues of this 2 by 2 matrix, omega naught, G root n, and that will of course have the form omega plus minus is equal to omega plus omega naught over 2 plus minus square root omega minus omega naught over 2 squared plus G squared n. And if you plot these energies as a function of G, or G root n, what you find is that one of them starts at omega and one of them starts at omega naught, and one goes down and one goes up. And at some point, this energy goes to 0. And what that means is that at that point, the energy of one of the kinds of excitation of this system about the ground state has become 0, and therefore that excitation will cost nothing to create, and then you'll get lots of them. So at this point when omega minus goes to 0, the number of excitations C would start to diverge. Now what that really means is at that point, my approximation of replacing the square root by 2s will go wrong. So I know that beyond that point I have to do something else, but what it also tells me is that at that point I start to get this transition. This is the boundary where the transition to a state where the G dominates over the omegas, and you start to get coherent light in the cavity. And actually you can see immediately what value that requires. It's the value where the determinant of this 2 by 2 matrix is 0, because if the determinant is 0, one of the eigenvalues will be 0. And so this is the value omega naught is equal to G squared n. And so this is the location of the phase transition in the rotating wave approximation, i.e. in the Tavis-Cummings model. I can generalize this to what happens for the Dicke model with slightly more work, but no new concepts. The case for the Dicke model, critical value will still be the same because The quadratic problem will be the same. The point is that what higher orders will get you is the fact that these bosons interact, so that when you start to have a large... So it's perfectly allowable to have a negative energy of one of the modes as long as there was some positive interaction to stop the Hamiltonian being unbounded from below. So what it means is that this ground state of the model, the ground state of this model is no longer straightforwardly a state with no excitations in it. When omega plus and omega minus are zero, the ground state of this Hamiltonian is the empty state with no excitations. At the point that this mode touches zero, actually there are many possible ground states. Any number of excitations in the C mode would, at least in this approximation, be a possible ground state. When it goes negative, it would tell you the ground state was infinitely negative energy and you could have an infinite number of excitations. That infinity is all because I forgot the higher order terms. And I'll come back and treat those in a moment. So it depends on the values of omega and omega naught and how far apart they are, as to whether you can believe the phase transition is in a regime where the rotating wave is still good. The way I should phrase this really is, there are versions of this problem that I will come back to in later points in these lectures, where the Tavis-Cummings is really the right model. The phase transition of the Dicke model is not well described by using the Tavis-Cummings model. I'm about to say what happens with the Dicke model, and it will give you a different location for the phase transition, and therefore the Tavis-Cummings rotating wave is not a good approximation for trying to treat the phase transition of the Dicke model, but there are physical situations where the right model is the Tavis-Cummings model, due to other bits of physics that leads to this effective Hamiltonian. Right, so as I said, the other thing I should then do is say what happens if I think about the Dicke model rather than the Tavis-Cummings model. And what that means is I get the same first two terms in my Hamiltonian, omega naught b dagger b plus omega a dagger a. But now this last term is no longer straightforwardly create a photon and de-excite a spin and vice versa, but it has a plus a dagger times sigma x, and sigma x is sigma plus plus sigma minus, so this turns into b plus b dagger times a plus a dagger. And so I get two extra terms here, ab and a dagger b dagger, that create or destroy pairs of excitations. And what I should then do is the same thing as before, diagonalize this Hamiltonian in order to find what the normal modes are, and it will again be possible to write it in this form of two bosonic modes. And the reason I know I can do that is that it's still a quadratic Hamiltonian. There are various levels of complexity of how I can do this. The thing I think is simplest to do is to realize that this is a problem of two coupled harmonic oscillators, solve the problem of two classical harmonic oscillators, and then re-quantize the answer. And what that means is I should say, let me write the operator A as 1 over square root 2 omega, omega A plus, omega X plus IP. And the point about this is that the commutator of X and P being equal to I is equivalent to the commutator of A and A dagger being equal to 1. So this is just recovering the standard commutators of quantum mechanics. I've set h bar everywhere equal to 1 through everything I'm saying, so that's why there's no h bar here. And the form that I have chosen here has a rather specific structure, which is such that when I stick this into here, I will get a term in the Hamiltonian that looks like p squared with no factors of omega. And I know that this is a trick which will make life easier, and I'll do the same for the other mode. I would like to look at this and put the right factors of omega naught such that I will get a term q squared with no factor of omega naught. Because if I write things this way, the Hamiltonian will become p squared plus q squared over 2, kinetic energy term, plus omega naught times y squared plus omega, sorry, I have lost a factor of 2, half, omega times x squared, and this last term here, if I stick it inside this thing with a factor of a half in front of it, ends up looking like 4g root n xy. And so the point about writing this all this way is what I have is two masses which are in a potential which looks like y squared and x squared and this xy cross term. And if I diagonalize that 2 by 2 classical problem, I could then quantize everything and then return to rewrite it in terms of raising and lowering operators. But I don't really need to do that. If all I'm interested in is where is there a mode with zero energy, then what I should do is just find out what is the condition on this classical problem having a mode of zero frequency. So I will do that. I'm going to save this blackboard, and so I will skip past it because I want to come back to that one later on. You can, yes. This is the cryptic comment saying there are various levels of how complicated I can make the diagonalization of this. So of course, you could just write down there as a 4x4 matrix with a Hopfield-Bogolubov structure. To me, that's fine if you know what the structure of that matrix should look like. But the great advantage of this is it doesn't require any intuition. I've just said, actually, it's a classical problem I know already how to solve, and I could do it for however many coupled modes I had. Okay. So if I solve that problem, the classical problem I have to diagonalize involves diagonalizing a 2 by 2 matrix, which has this structure. And now it looks very similar to what I had before, except there's an extra factor of 2. And so that extra factor of 2 tells me that actually for the Dicke model, the phase transition occurs when omega naught is equal to 4g squared n. And so this is the comment I made a moment ago, that the Tavis-Cummings model predicts the wrong phase transition. If you're trying to use that as an approximation for the Dicke model, the real phase transition is at this point when omega naught is 4g squared n. Okay. So I want to comment very briefly on what can you do beyond the phase transition, and then I want to try to say something at the end about what might prevent this phase transition actually occurring. So beyond this phase transition, I can no longer make this kind of square root expansion because one of the modes went negative and I shouldn't trust that approximation. There are a whole variety of different things I could choose to do. Yes, well, the rotating wave approximation was really based on G being small compared to the sum of omega and omega naught, and this condition. Well, so rotating wave approximation was really good because G was much less than omega plus omega naught, or G root n. And it's pretty clear that this is telling you that actually G is on the same scale as omega. So the transition occurs in the range where G is on the same scale. So yeah, if the Tavis-Cummings model came because you made a rotating wave approximation, it is indeed no good. There are cases where you could really derive the Tavis-Cummings model, but that's slightly more subtle. Okay, yeah, so there are many things I could do beyond the phase transition. I'm going to do what I think is the simplest to consider, or the simplest to do the math for, which is to say, let me consider an ansatz state. And my ansatz will be that I have a coherent state of the photons with some real coefficient alpha. So this creates a coherent state in the photon mode, and I will just say that there is some spin state, because as will become clear in a moment, I don't really need to make any further approximations. If I say that I have this coherent state, the great thing that allows me to do is say that that there'll be some effective Hamiltonian where I put in this variational state, and it will be that I can replace all photon operators by alpha by some classical operator, and then what I get is an effective Hamiltonian, which looks like omega mod alpha squared plus B dot S, where B is an effective magnetic field whose X component is 2G root N alpha, and whose Z component is omega naught. Sorry, I've got that wrong, I think. Let me check. Yes, so there's no root n, and there is a factor of 4. Yeah, there's a factor of 4. Why do I think there's a factor of 4? This sigma turns into 2sx, so there's a factor of 2 from that, and then there's a plus a dagger, so it's 2 alpha, so indeed the field that you see in the X component coupling to the spin is 4 lots of G times alpha. And then in the Z direction you just get the omega naught. And the great thing about this is clearly this is an easy problem to solve. I have a spin in a magnetic field. The ground state is to make the spin point along the direction of a magnetic field. And so the energy will look like omega alpha squared, if I assume alpha is real, minus the length of the spin, which is n over 2, times the magnitude of this magnetic field, which is omega naught squared plus 4g squared, plus 4g alpha all squared. And what you can do with this energy as a function of alpha is see that as you increase the value of g, for small values of g, the energy goes like this. The optimal value of alpha is 0. As you increase g in this term here, what it will start to do is make this dip down and have its lowest energy state be at some finite value of alpha. And all you then need to do is to say, what is the solution of dE d alpha being equal to 0? And that will tell you what the critical value, what the value of alpha is. Just due to shortness of time, I'm not going to work through that and just say that what that gives you is that the optimum coherent field looks like Ng over omega times 1 minus G critical over G to the 4, where G critical is the value of G we found that the phase transition occurs at. So what this then predicts is that the value of alpha you should have is 0 up to critical G, and then increases as you go above that point. Okay, so I'm doing the Dicke model in all of this because I have this factor of 2 here. In the Dicke model, there is no phase freedom because this is really coupling to A plus A dagger, and so there is a sign freedom, which is whether I take the plus or minus square root, but there is no phase freedom. If I did the Tavis-Cummings model, then yes, there's a phase freedom, but as we saw, Tavis-Cummings is not good in this phase transition region. Yes, so this is where I have just made the replacement because of saying this is a coherent state, but not done nothing with the spins. So actually one great feature of this kind of ansatz is you could also use this for finite temperature cases or dynamics of the spins, as long as you assume a coherent state. The problem for the spin dynamics becomes very straightforward. Yeah, it's a mean field approximation. It's or a semi-classical approximation as well. There are many ways to think of where this comes from. I mean, all I'm really saying by writing this is I have replaced A by alpha, and alpha is classical, and therefore I get a simple quantum problem to solve. Okay, so what I want to do in the last 6 minutes is to demolish everything that I've said so far by telling you this phase transition doesn't exist. And the reason that there is a problem with this phase transition comes from what condition we have really said is required in order to have this phase transition. So if I go back to where did the ingredients of this phase transition get scattered across the derivation, we know what value of G it is that we should have. And somewhere in one of the boards I erased, I had an expression for what G really was. G was really something to do with the strength of the vector potential associated with a single photon, multiplied by the sum over those charges within a single atom of Q alpha, P alpha over M alpha, and I took matrix elements of this between two states of the atom. And there's some subtlety in, but I've lost all the dependence on vectors and polarizations, but that doesn't cause any particular problem. What I can also do with this form of G is to rewrite it in terms of something that's a little more helpful in what I want to say, which is to rewrite this Q alpha, P alpha over M alpha by saying that this thing can be written as A times I times sum over alpha of naught times the commutator of the bare atomic Hamiltonian with Q alpha, R alpha. And why that is useful is that you can then expand this thing out and say what this will give you is minus omega naught times the matrix element of a thing that I can regard as what is the dipole moment of this transition. So this form here is very useful for rewriting this in terms of dipole moments, and the net result of that is, at least ignoring factors of I, which turn out not to cause any problems, the modulus of this G is equal to this A, the strength of the vector potential from a single photon, times omega naught times D01. And the phase transition that we have said we are going to consider occurs when this is large compared to something to do with omega and omega naught. I'll put this in quotes because I'm not going to get all of the factors right. And if that is large, then one of my starting approximations at the beginning of this lecture goes wrong. And that starting approximation was that when I wrote this term here, I said I'm going to throw away this final term in the Hamiltonian. And I threw it away because typically A squared is small. And A squared is small because both the coefficients, or the coefficients scale like the density of atoms, and under normal conditions, the density of atoms is not high enough for this to be a significant correction. But the strength of this last term, this is set by Q alpha squared over M alpha and the scale of A. And I can think that what this last term actually does is to add to the Hamiltonian an extra contribution which is going to become large in exactly the same circumstances as the phase transition occurs. What that means specifically is this last term in the original dipole gauge, or coulomb gauge Hamiltonian, should be written as saying the Hamiltonian, the Dicke Hamiltonian, should go to the Dicke Hamiltonian plus a term that looks like sum over all atoms of some coefficient psi times A plus A dagger squared, and this coefficient psi should look like the sum over all charges in an atom, Q alpha squared over 2M alpha, times the strength or vector potential associated with the single photon, all squared. And if I make that change to the Hamiltonian, then actually what this does is says when I think of coherent states of photons, I have increased the energy of the photon mode, and I've increased the energy of the photon mode by an amount that scales with the number of atoms. This is the diamagnetic contribution of a single atom to the physics of light in the cavity, and its contribution is that when I write something like this expression for E over here, that wherever I had omega appearing before, what I will now get is that omega goes to omega plus number of atoms times psi times 2 alpha all squared. And so the condition for the phase transition to occur is really not omega naught is 4mg squared. It's that 4ng squared has got to be greater than omega naught times omega plus 4n psi. So there shouldn't have been an alpha there, or I should have written that as alpha with alpha squares in all of that. So that I should be able to just say there is effectively some atom-dependent renormalization of the cavity frequency due to this diamagnetic shift. So this could look like a minor correction, but the problem is it relies on a particular statement about the properties of atomic dipole moments, because if I look at the dominant terms on both sides of this equation, this can only be true if the large n limit of both sides is true. If n goes to 0, it's clear that the left side is 0, and so the inequality can't follow. So this requires that g squared has to be greater than omega naught psi. That's a minimal condition. It's not actually sufficient, but it's absolutely necessary. And we've just worked out what g is, and we've worked out here what psi is, so let me put those in. I need that this calligraphic a squared times omega naught squared times d naught 1 squared has got to be greater than the right-hand side of this, which is omega naught, times this combination q alpha squared over 2m alpha times a squared. And I can cross out the a's, and I can cross out one of the omega naught factors, and I have a condition then that says the dipole moment of one atom must be greater than this quantity. Now, the problem is I can prove that exactly the opposite is true, and this will take me another 5 minutes. Do I have 5 minutes? Okay. So where shall I do this? If I erase this board, is everyone happy? I want to leave what I just wrote, and I want not to be looking at opposite sides of the board. So the problem we have got this down to is we would like to prove whether or not I can have omega naught d naught 1 squared greater than the sum over alpha of q alpha squared over 2m alpha, where I should remember that what d naught 1 means is the matrix element between state naught and state 1 of the sum over all charges of an atom of q alpha r alpha. And the statement that one needs in order to prove this is something called the F sum rule, or Thomas-Reich-Kuhn sum rule, or several other names. And I will write it in terms of this combination here being called D, and it relies on working out a quantity which I'll call X, which is the double commutator of D with H atom and D. And there are two ways I can go about this. One way is to recognize that actually commutator of D with the atomic Hamiltonian is something I already previously used. It's written in terms of momentum because the commutator of R and P squared will give me factors of P. And if I work through that, and if I just work out all of these commutators, it turns out that this thing is equal to sum over alpha q alpha squared over 2m alpha. And so this is, of course, useful because this is the right side of the inequality that I want to prove. This just comes from this definition plus the statement that the atomic Hamiltonian depends on momentum like p squared over 2m. And once you have that, then you know that this is an equality for this quantity. The other thing you can do is say, well, now I know that this is just a C number, I could just calculate the matrix elements of this for any state, let me consider the ground state, and then stick this operator into this, and stick in a few resolutions of identity. And I can stick in a resolution of identity between the inner and outer commutators, so I'll put in a state n, d, naught here, and then I should write this all the other way around because there was a commutator. And what I can do with the right-hand side of this equation is to then notice that there are lots of things I can multiply out. Wherever I have this d H commutator, I can think of it as either H acts on an atomic eigenstate n or on an atomic state 0, and so I will just get factors of those energies, and everything else will just be matrix elements of D. So if I generalize get rid of this, I think. If I generalize the definition D01 to D0n for the matrix elements between state 0 and state n, and I introduce a quantity which I will call E0n, which means what is the energy of state n minus the energy of state 0, what's the energy transition, and I'll say that omega naught is E01. What I can do with this is prove that this expectation is equal to the sum over all excited states of E0n times D0n squared. And of course, I know that this thing is equal to the sum over alpha of Q alpha squared over 2m alpha. And I know what I want is that one of the terms in my sum, the first one, should be greater than the right-hand side of this expression. But this is definitely impossible because all the terms in the left are positive. So the best thing I could possibly do is to make only the first term in the sum contribute, and even in that case, all I will get is equality. There is no way that I can, from this, have any one term on the left-hand sum dominate the rest of the expression. And so what this says actually happens is if you include the diamagnetic term and you increase the matter-like coupling by increasing density of atoms or changing mode volume or something else, then this correction to the Hamiltonian, this extra term in the Hamiltonian, means that the energies of the normal modes do not go down to 0, but actually asymptotically approach 0 in the best case, and otherwise stay at something positive. And so this transition doesn't occur. And then what I'm going to talk about in my next lecture is how do you get around this? How can you find ways out of this no-go theorem? And there are many ways out. I'll talk about a few of them, but I'll leave that all for tomorrow. Thank you for your attention.